Session. Yeah, nice to see you here, and it's very nice to see our first speaker today. Yeah, Dr. Giacomo Sorelli, and let me introduce. I told you that today maybe is intrigue about either we can see a coin from the space, could be resolved finally. I believe, yeah, Giacomo.
Yes, hopefully.
Yeah, because it was a very large discussion in Ukrainian segment of Facebook when we announced this conference. And some people thought that we don't believe it. Yeah, today we will listen from the third hand whether this possibility is possible. Okay, let me introduce our speaker. Dr. Giacomo Sorelli has graduated with master's degree from the University of Florence in Italy, and he did his PhD in the University of Freiburg in Germany. In the University of Florence, his master's degree was related also to quantum metrology, yeah. And in the University of Freiburg, he was doing with propagation of quantum light through complex systems. And after that, Giacomo Sorelli had a very good experience in laboratory Castel Brosset. This is University of Sorbonne in Paris, France. Yeah. And where he got also even more experience in quantum metrology and super-resolution imaging. And now Giacomo working for the Fraunhofer Institute in Germany. That is it's a very well-known and famous institute in Germany, dealing also with optical different problems, with imaging problems in particular. And he's working there as a group leader of a young researcher with ERCIN grant, which is very prestigious grant program in the European Union. And today, I believe Dr. Giacomo Sorelli will talk us about super-resolution imaging, this fascinating technique that you need all your knowledge you had before, in particular from the lecture by Professor Gerard Ariesa. And please don't hesitate, ask questions during the lectures. It's possible? Is it possible?
Of course, of course.
Yeah. Just raising hand. I will be here and see how you're raising hand. And my colleague Anton Svetlichny will help me with online audience. And after lecture, we will also have some question and answer session. Okay.
Very good.
Yeah. Giacomo, audience is yours.
Thank you. Let's see if I can...
Yeah.
Can you see my screen now?
Yeah, we can see everything is perfect.
Okay. Screen, turn on the pointer. Okay. Thank you, Andrei, for the nice introduction and for inviting me to give this lecture in this school together with many other excellent teachers. And on the first day, you heard about measurement theory and classical parameter estimation, and then Gerardo gave you a lecture on the quantum parameter estimation. So I think you have a great background to follow what I'm going to talk about today, which is the multimode quantum optics approach to super-resolution imaging. I will start by giving some motivation about why we want to do this. And then I will present some theory on how we describe modes and quantum states in quantum optics. Then we'll go deeper into quantum metrology and see how we can use quantum bounds as resolution limits. Then I will present a practical method to approach these resolution limits that come from quantum metrology. I will discuss a bit about an experiment that we did on the subject, and if there is time, I will present some additional results on that goes beyond incoherent sources and separation estimation. So let's start with motivation. I want to talk about super resolution, but let's start take a step back and say what is optical resolution. And a very end wavy and simple definition would be that resolution is the ability to tell point in space apart. So you would say that this video here on the left represent unresolved objects. You just see a bunch of wandering blobs, while this one on the right, where you see the single objects, you would say that it is resolved. And historically, resolution has always been connected with diffraction. Basically, the point is that if you have a point source in the object plane of your imaging system, being it a microscope or a telescope, diffraction causes the image of this point source to take the shape of an airy pattern, which is a broad shape. It's not a point. You have this inner disk, which is brighter, and then you have these fainter rings that appears on the outside. An airy disk is given by this intensity distribution with a Bessel function divided by AR, where A it's a quantity that gives you the width of this disk, and it's related to the numerical aperture of the imaging system and the wavelength of the light. The numerical aperture has to do with the size of your imaging system, of the collecting aperture of your imaging system, D, and its focal length, F. And in the following, I will always approximate this airy disk with a Gaussian, and this approximation looks like this, where the width of this Gaussian is of the order of 0.42 lambda over NA. So we see that if we have an imaging system with a very large numerical aperture, then this Gaussian has a very sharp peak, and so a point will look more like a point, but it's always broad and it never looks like a point in the image plane. Probably one of the most famous classical resolution criterion is Rayleigh criterion, which was proposed by Lord Rayleigh in 1876. And this criterion tells us that two sources are resolvable if the first minimum of the airy disk formed by one source coincides with the maximum of the airy disk from the other source. And this gives us a minimal resolvable distance, which is of the orders of 1.5 the width of this Gaussian. So at the Rayleigh distance, the two sources are distinguishable because we can see two peaks. If we go below the Rayleigh distance, we see single peak, and if we go far above the Rayleigh distance, we can see two well-distinguished Gaussian shapes. There are other criteria that were proposed more or less at the same time in different regimes. For example, the Abbe criterion was proposed for microscopy, and simply says that the minimal resolvable distance is half the wavelength renormalized by the numerical aperture of the imaging system. Or the Sparrow criterion was proposed some years later, more in astronomy, and these tell us that two sources are resolvable if here in the center there is a minimum. So the smallest separation for which there is a minimum can be computed, and it's of the order of 1 width of this Gaussian. However, all these criteria are kind of end wavy visual criteria. So they are based on the idea that yes, the point source diffract, but and then we find some visual idea to say when the two sources are distinguishable. But these are not fundamental limits. So there's nothing that tells us that we cannot go beyond this diffraction limit. And in fact, in the past 20, 30 years, there have been development of many techniques to go beyond the diffraction limit. And these techniques are called super-resolution techniques. However, these techniques are mostly domain specific. So for example, there are techniques which are widely used in microscopy. And the main idea of this technique is to avoid that two sources which are too close to one another emit at the same time. And this is generally done by using high power laser to deplete emission from some part of the sample. And so this requires to prepare your sample in order that the emitters are distributed in a certain way and then can be activated and deactivated using a certain kind of illumination. And of course, these are active techniques that rely on particular ways of illuminating your sample. Despite this limitation, these have been very successful, and Morner, Hell, and Betsy got the Nobel Prize in chemistry in 2014 for these techniques. On the other hand, there are super resolution techniques which are used nowadays in remote imaging or astronomy settings. These techniques are, of course, passive because you cannot control the object when it is very far away. So you have to rely on the light that naturally is emitted or reflected by the object. And so these are generally very numerically, computationally heavy techniques. They rely either on recombining images coming from multiple telescopes, or not on intensity measurements, but full field kind of measurements that can be used to apply complex deconvolution algorithm that can be used to enhance the resolution. So what we would like to have is a super resolution technique that it's not domain specific and that works at all length scale. So a super resolution technique that we can use both in microscopy and in astronomy, for example. And so if we want it to be used in microscopy in a non-invasive way, so without shining high-power lasers to our sample, and also usable in remote applications, then we need this technique to be passive, so that it requires no interaction with the sample. We would like it to be linear optical, so that only requires linear operations, which are generally cheaper and provide simpler experimental apparatus. And I will maybe come back to this point at the end of my lecture. We would like these to be compatible with any kind of sources, independently of their degree of coherence, so that these to be usable both in coherent and incoherent imaging. And the main observation that lead us to finding a technique that can satisfy all these points is that, as I said, the diffraction limit is not a fundamental limit, and the simple shape of the point spread function doesn't tell us everything about the resolution of the apparatus, and there are many other points that comes into play. For example, the noise of the light that we are looking at. And so we need a way to find fundamental limits. And a way to find fundamental resolution limits and possibly ways to reach them is to use the tools of quantum metrology and multimode quantum optics. Now we can move to the second part of this lecture, where since we want to use multimode quantum optics and quantum metrology, I would start by reviewing some important concepts in multimode quantum optics. So first of all, what's an optical mode? So optical modes are transverse solutions of the wave equation. So they solve the wave equation and they obey this transversality condition. And when we take many optical modes, we'd like them to be orthonormal, so that a complete set of orthonormal modes give us a basis for the space of solution of the wave equation. And if we consider the optical modes associated with all different degrees of freedom of light, then we can always describe light in terms of these optical mode components. So we have modes associated with polarization. Different bases for polarization could be horizontal and vertical, or right and left circularly polarized, or diagonal and anti-diagonal polarizations. Or we can have spatial modes. Here I have some examples of Laguerre-Gaussian and Hermite-Gaussian modes. And we have time frequency modes. Since in this lecture I want to talk about imaging, and images only deal with how light is distributed spatially, I will only focus on spatial modes. And in the next 3 slides, I'm going to give basically a short summary on what's the main concept in this presentation, and then we will go further into details why spatial modes are relevant for imaging. So usually we think about images in terms of pixels, because we are used to acquire images with cameras, and a camera measures the intensity of light at each pixel. But as we see in this animation here, we can reconstruct an image by decomposing light into an arbitrary spatial mode basis. So here, for example, I'm adding 1 by 1 different Hermite-Gaussian components. And if we stop at the last frame of the video, here we see these 2 reconstructions that have been done using the same number of pixels and, in this case, Hermite-Gaussian modes. And we see that, I mean, both reconstructions are effective to a certain extent and have different features. So we see that the pixels gives this pixelated kind of nature that we are more used to see, while the Hermite-Gaussian modes, for example, since they are extended all over the transverse plane, they are better and getting these curved shapes, for example, the elbow of the photographer. On the other end, I don't have modes that extend to the corners of the image in this case. So here I cannot reconstruct the corners, and I get this kind of wavy behavior. If I use more pixel or more modes, I would get 2 images which are both sharps. So the question that we want to answer is there a basis which is best to reconstruct images that we can use to extract more information from an image? And for these kind of complex images, it might be hard to give a definite answer. But if we look at simpler problem, then we can give a simple answer and a clear answer. So if we now look at a single point source in the object plane, we have already said that when it propagates to the image plane of our imaging system, we obtain a broad intensity distribution. And if we measure this intensity distribution with a camera, then we get this kind of blob here. On the other hand, if we demultiplex into a specific mode basis, I will say more about which mode basis and how we choose this mode basis in the following. But what we get is that if we have a single source in the object plane, we get a signal only in 1 mode. On the other hand, if we have 2 sources which are very close to one another, then when we look at them with a camera, we don't see any difference between this image and this image. On the other hand, if we look at the multiplexing into spatial modes, we see that now the signal in this fundamental mode got a bit smaller, and the signal in these 2 modes appeared. And in fact, the population of these modes are very sensitive to the presence and the position of the sources. And in the following, I will try to make this statement more quantitative. To do that, we need to start by saying how we describe quantum light in different optical modes. So we say that optical modes form an orthonormal basis of solutions of the wave equation. And so this means that we can express the electric field as a complex superposition of optical modes. So we have an arbitrary electric field here. I'm just focusing on the spatial part, and this is given by a complex superposition of spatial modes with some complex amplitude. So in classical optics, the state of light in each optical mode is given by a point in this complex plane. When we turn to a quantum description of light, what we do is to associate with each mode a quantum harmonic oscillator, where now we have replaced these complex coefficients with the quantum operators. And in particular, we have these creation operators that creates excitations of these harmonic oscillators, which we interpret as photons per mode. So each energy level of the quantum harmonic oscillator in each mode correspond to 1 photon, 2 photons, and so on. So this creation operator creates photons, so excitation of each mode. And we can define quadrature operator, which are the analog of the real and imaginary part of the complex amplitudes. Now we have this kind of real and imaginary part of the creation and annihilation operators. And these are like the position and momentum operators for the quantum harmonic oscillators. And as we know from the quantum harmonic oscillators, these are two non-commuting observables. And since they do not commute, they obey an Heisenberg type uncertainty relation, which means that now the quantum state for each mode is not defined by a point in this complex plane, but is defined by a probability distribution, a broad distribution with a given width. And an important aspect is that even if the amplitude is 0, so if the quantum state in a mode is the vacuum, then this kind of noise always remains. So we have some quantum noise also in the vacuum. And we will see in the following that quantum noise of modes which are in vacuum has an important role on sensitivity limits and so on, also on ultimate resolution limits in imaging. So we established that we have a superposition of optical modes and that we associated an harmonic oscillator to every mode, and we now populate these modes with photons. So a general pure multimode quantum state can be written like this, where N1 U1 means that I have as a quantum state with n photons in mode U1. And the general pure quantum state then is a superposition of a certain number of photons in certain number of modes. Of course, general state quantum states are not pure. They can be mixed, and the general mixture will take this this form here, where we do not only have photon number diagonal states, so states with a definite number, superposition of definite numbers of photons, but we have also some off-diagonal terms describing some coherences between terms with different numbers of photons in a given mode. These general states are quite complicated. So for the rest of the lecture, we will focus on states where we have at most 1 photon per mode. So this can be written like this. So we have a vacuum components, which is predominant. So this is a state where all modes are in vacuum. And then here we have a superposition of single photon states in each mode. So here I don't have these products anymore because I'm considering that only one mode has one photons and all other modes are in vacuum. So we consider these simplified kind of states. And when we measure, so as kind of measurements, we will always consider kind of photon number counting measurements. And for these kind of states, counting photons means detecting either one photon or no photon in a specific mode. So what we ask ourselves is what's the probability of detecting one photon in a mode Fk of R. And note that this mode Fk, it's a general mode. It might be different from the modes that we use to describe our states, which here are these modes Uj. And so this probability of detecting a photon in a mode, it's given by the trace of the density matrix describing our quantum states multiplied by the projector of on a single photon state in mode Fk. And if I replace this expression from rho in here, I get that the vacuum contribution, the vacuum term doesn't give any contribution, and I get a contribution only from this term here, where I have these weights here, rho j times this superposition. So what we ask ourselves is how do we compute this overlap? So this is overlap of a single photon state in mode Fk times, so scalar product with a single photon state in mode Uj. And to compute this overlap, we go back to this expansion of the electric field operator into different mode bases. So we can expand the electric field in an arbitrary mode basis. So here we consider the expansions in terms of the modes Fj with associated annihilation operator Bj, and the expansion in terms of the, let's say, original mode basis Uk with associated annihilation operators Ak. Now we say that these optical modes, they form a basis on the space of solutions of the wave equation, and we know that we can change bases by applying a unitary transformation. So we can express arbitrary modes in terms of modes of a different basis, and the coefficients of this expansion are given by the elements of this unitary matrix, which are just the overlaps between the elements of one basis with the elements of the other basis. Now, if we replace this expansion into this expression here, we have that basically we found a way to transform the annihilation operators B in terms of the annihilation operators A. So we have that this unitary transformation of optical modes induce an analog unitary transformation on the quantum annihilation operators, which means that we can express a single photon in mode UK as a superposition of single photon states in modes Fk, where the coefficients of this superposition are given by the elements of this unitary operator. So if we go back up here and we substitute this expression here, then we obtain that basically the probability of detecting one photon in mode Fk is fully determined by these overlaps between the expansion of the different modes. And now we're going to use this general expression to look at the particular measurements for the kind of state that we are interested in, which is the quantum state of 2-point sources in the image plane of diffraction limited imaging system. And in particular, we're going to consider two equally bright sources. So these two sources have the same intensity, and they are separated by a separation d in the object plane. We considered an imaging system with a Gaussian point spread function, so that source at position 1 will be mapped into a shifted mode at position when u0 plus d halves, and the source at position minus d half will be mapped into a shifted mode at position when u0 of x minus d halves. And then, as we say, we consider this approximation where we detect at most one photon in the image plane, one photon per mode. So the quantum state in the image plane is given by this vacuum contribution with weight 1 minus 2 epsilon. And then we have this equal mixture of one photon in mode u1, which means it's a photon that comes from this source here, or a photon in mode u2, which would be a photon that comes from this source here. Now we start by looking at the standard measurement that one would do to detect, to look at this quantum state, and this would be measuring it with a camera, so to performing detections in the pixel basis. And for simplicity, we will take a continuous limit. So we imagine that we have a camera with infinitely many and infinitely small pixels. And so the probability of detecting a photon at position X for this kind of measurement will look like this. So like we have this epsilon coefficient, which is the probability of having one of these two single photon states, and then this is an incoherent superpositions of the intensity of mode U1 and mode U2. So here we basically have a probability interpretation of what one normally gets when one does intensity measurements, and we go back to the Rayleigh kind of criterion scenarios, where if d is very small, then this probability has a single peak, and by increasing d, this probability distribution will get two peaks at the position of the two different sources. Now let's look at a different measurement, which is a spatial mode multiplexing measurement, which we abbreviate with SPADE. And in particular, we will consider a spatial mode multiplexing measurement in a basis which is constructed from orthogonalized derivatives of the point spread function. And now the point spread function, so the shape of the image of a single source in the object plane, is a Gaussian. And if you take derivatives of a Gaussian, successive derivatives, and you orthogonalize them, what you obtain are the Hermite-Gaussian modes. So where you have the Gaussian envelope multiplied by an Hermite polynomial. And now the probability of detecting a photon in one mode of this basis for two sources at distance d, this is given by, again, epsilon, which is the weight of the single photon part from this state, multiplied by this incoherent superposition of these amplitudes beta k, where betas here are the overlap between the Hermite Gaussian modes, and the images of the two sources shifted at the position plus minus d. And these overlaps takes this form here. Now, if we look at these overlap here, and we consider a kind of Taylor expansion of these modes here, these shifted modes, we have that a shifted mode is composed by the unshifted mode, and then depending on the position of the source, plus or minus a term which is proportional to the distance between the sources divided by the width of the point spread function times a component which has the shape of the first derivative mode. So if we compute these overlaps on this first derivative mode, then we will obtain a population or a term which is proportional to the separation between the sources. So we expect that projection on this derivative mode to be very sensitive to the parameters we are interested in, which is the separation between the two sources. And let's try to make this quantitative now, how sensitive the two different measurements, so the direct detection measurement and the mode projection measurements are for estimating this parameter, the separation between the two sources, and we do that by using tools of quantum metrology. So you probably heard many times in this week about the Kramer-Rao lower bound. Now, for the moment, we are considering the classical Kramer-Rao bound, which tells us that the variance for an estimator, for an unbiased estimator of the parameter of interest, in this case, the separation between the two sources, is always larger or equal than 1 over the Fisher information for the estimation of this parameter. And as you know, the Fisher information, the classical Fisher information, depends on the kind of measurement we are performing. And in particular, in our case, we want to consider when we are performing repeated measurements on m copies of the quantum state we were considering before. And if we consider direct imaging, which is a continuous measurement, as we said before, we are considering infinitely many, infinitely small pixels, then we can take this definition of the classical Fisher information as an integral over the square derivative of the probability distribution for detecting a photon at separation at position x when the separation between the two sources is d, multiplied by 1 over this probability distribution. And as we have seen a moment ago, this probability distribution takes this form here. And since we are considering m copies of the state, then we have this Fisher information here, which is multiplied by m here. And we also introduced this parameter here, which is the total number of detected photons. And this is given by the weight of this single photon component here. Actually, there should be a 2 here because you could have 1 photon from here or 1 photon from here. Anyway, if we now look at this expression for the Fisher information as a function of, so just to be precise, this is the total number of photons coming from one source. And since there are 2 sources, then here I'm renormalizing the Fisher information by 2n and also rescaling it with the width of the point spread function. And what we see here in this expression for the Fisher information is that for large separation, the Fisher information has this constant asymptotic value. But for small separations, the classical Fisher information goes to 0. And it goes to 0 like the separation squared. And this vanishing value of the classical Fisher information for estimating the separation between two incoherent sources was first noticed in this paper from Monkey-Tsang in 2015, and Monkey named this effect the Rayleigh curse. So it's a parameter estimation version of the Rayleigh limit. So the Rayleigh limit tells us that we cannot resolve two sources which are too close to one another, and this Rayleigh curse tells us that the reason why we cannot do that is that the Fisher information for estimating the separation parameter is vanishing for small separation. Now let's look at the other measurements we were looking at before, which is SPADE, so spatial mode multiplexing. In this case, we have a discrete measurement, so we measure intensity in a number of discrete modes. And so we now express the Fisher information not as an integral, but as a sum. And now we have the probability distribution for detecting one photon in mode UK when the separation between the two sources is D. And we have seen that we can calculate this probability distribution in terms of these modes overlap here. And now if we plug this expression into this sum and we take a sum over the full basis, so infinitely many modes, what we get is that this is equal to W squared over 2n. So if we fix the number of detected photons, then we have a constant value of the Fisher information. This means that we have a Fisher information that is independent on the separation. So we have no Rayleigh curse anymore, and we can achieve the same resolution. So we can estimate arbitrary separation, no matter if large or small, with the same variance. And so what we can ask ourselves is this then the ultimate resolution limit? So is this the best we can do, or there are other measurements that can do better than SPADE? And as you've probably seen many times this week, if we want to look at the ultimate sensitivity limit, which in this case we call the ultimate resolution limit, we can look at the quantum Fisher information. So at the quantum Kramer-Rao lower bound, which says that the variance for the estimation of a parameter for an arbitrary measurement can never be smaller than 1 over the quantum Fisher information, where the quantum Fisher information is the Fisher information optimized over all possible measurement allowed by quantum mechanics. This quantum Fisher information can be computed starting from an expression of the density matrix in terms of its eigenstates. So we can diagonalize. If we can diagonalize the density matrix, then we can compute the quantum Fisher information using this formula here, where here we have the derivative of the density matrix. Now, let's look at how we can find this expression here, this diagonalization of the Fisher information in our case. So we started from this expression here, when we have this vacuum contribution and this contribution from the two modes at position plus minus d over 2. And what we see here is that these two modes are overlapping. So this is inconvenient if we want to write an expression like this. So this is in a way of saying this expression looks kind of diagonal, but it's not really diagonal because the information contained into these two overlapping modes are partially overlapping. So if you want to write an expression which is really diagonal in a sense that each term of the sum contains information which is not contained in the other terms, then we have to expand this term in terms of orthogonal modes. And we can do that by taking the symmetric and antisymmetric superposition of these two modes. So we just take the sum or the difference of the two modes, and we normalize this sum of difference with this term here. So this is the sum of the modes, this is the difference of the modes, and this delta here is the overlap between these two modes. So with this superposition and with this normalization, we have obtained two different modes, U plus minus, which are now orthogonal and normalized. And we see that before this was expressed as an equal superposition of two single potent states into overlapping modes. And now we have an unequal superposition of two single potent states into non-overlapping modes. And these the weight of these, well, I said superposition is, it's not the best term. I should call this mixture. This is an unequal mixtures of a population of the symmetric mode and the antisymmetric modes. And the weight in these mixtures are given by 1 plus the mode overlap and 1 minus the mode overlap. So now we have this expression here for the density matrix, and we can expand this derivative here, and we obtain this expression for the quantum fissure, where now we have this term here, which looks like a classical fissure for these probability distributions in the mixture, plus this other term where we have overlap between the eigenstates of the density matrix and their derivatives. And if we look at these probabilities here in our state, we recognize that we have this, can have this P0, which is the weight of the vacuum contribution, and this plus minus probability, which depends on the separation through this mode overlap delta here. And so if we want to compute this term in the expression for the quantum fissure information, this will look like this. So if we want to get the full quantum fissure information, now we have to compute this other term here. And in particular, we want to look at how to compute this overlap between eigenstates of the density matrix and their derivatives. So basically what we have to compute, now this eigenstate of the density matrix are these modes here. So vacuum, and in particular, these single photon states in the plus minus modes. So what we want to compute now is this derivative of the single photon state in the plus minus modes with respect to the separation between the two sources. And you see that, the fact that this is a single photon state does not depend on the parameter, but what depends on the parameter is the mode where this single photon is. So these two photon, these modes, U plus minus, they change as I make the sources farther away one from the other. And we can compute this derivative by noting that these changes with respect to the parameter, they can be described as a unitary transformation of optical modes. So I can always map basis of mode at a given value of a parameter into a basis of modes at a different value of the parameter by using a unitary transformation between mode bases. And this unitary transformation between mode bases induces a Schrödinger-like evolution of the quantum states in these modes, where the Hamiltonian for this kind of evolution as this term here, which removes one photon from one mode and create photon into a different mode. So it kind of describes a tunneling of photons from one mode to another one, and the weights of this term are given by overlaps of modes with the derivative of these other modes, or from these modes which is removed, where the photons are removed with respect to the parameter. In particular, we can now divide this Hamiltonian into two parts. So we have a part here which is related to the modes plus minus, and we call these modes plus minus the initially populated mode, because for a fixed value of the parameter, all photons are in these two modes. And then this other part, which is related to other modes of the basis that we use to complete U plus minus to a complete orthonormal basis. These modes are for a fixed value of the parameter, all in vacuum. And so we separate the Hamiltonian into a contribution from the initially populated mode and the vacuum modes. Now, for this particular problem, the modes U plus minus, they are orthogonal to one another. We constructed them to be orthogonal to one another, but they are also orthogonal to their derivatives. So U plus is orthogonal to its derivative, but it's also orthogonal to the derivative of U minus, and vice versa. So this part of the Hamiltonian which relates to the modes which are initially populated, it vanishes. And so here we get that the sensitivity, it's fully determined by these modes here, by this part of the Hamiltonian, which only involves modes which, for a fixed value of the parameter, are in vacuum. So as I said before, when I was quantizing the electromagnetic field, even when a mode is in vacuum, this mode conserves its quantum noise. And as we see here, it's really just the quantum noise from these modes in vacuum that enters the sensitivity for the estimation of the separation parameter. And so in particular, if we now take this expression here and we plug in this guy here, we obtain this expression for this part of the quantum Fisher information. And as we said, these modes are orthogonal. The derivatives are orthogonal to the modes. So this part simplifies, and we obtain only this part where we have basically the modulus square of the derivatives of the plus minus modes. And to do the calculation, we get this term here. Now we can put all pieces together So we sum this part here with what we obtained from this term here. And we consider also m copies of the state, and we find this expression for the quantum Fisher information. And if we now compare what we obtained for spade with the quantum Fisher information, we see that they coincide. So not only spatial mode multiplexing gives us this beautiful constant quantum Fisher information that allows us to resolve arbitrary small separation with the same sensitivity as arbitrary large separation, but it's also the quantum optimal measurements that separates the quantum Fisher information. Okay. Now we have set the ground. We said what are the ultimate resolution limits and what's the measurement that saturates these ultimate resolution limits. What I want to discuss now is a practical method, so a simple estimator that we can use to reach this ultimate resolution limit in practice. And as we will see in a moment, it will not really allow us to reach the ultimate resolution limit, but the practically relevant resolution limit. So the simple estimator I want to talk about is what is known as the method of moments. So let us consider the scenario where we measure a single mode now. And we perform mu measurement in this single mode. And for each of one of these measurements, we obtained a measurement result, x1, x2, x mu. And then we compute the mean value of all our measurement results. And we compare this mean value with a calibration curve. This calibration curve could have been acquired by performing a calibration experiment, or maybe we have a very good model of our experiment and we can build this calibration curve from theory. And so we then compare the mean value of our measurement results with our calibration curve. And we say, okay, I obtained this value. It means that my value of the parameter must have been this one. This is very simple estimation procedure. And then we ask ourselves, what's the error that we make on our estimation? And this we can obtain simply from error propagation. So we have an error bar of our measurement on our measurement results, and could be the variance or the standard deviation around this mean value obtained from these mu measurements here. And then we propagate this error through the calibration curve, and this maps into an error on the estimator. And the error propagation formula is simply given by the variance of these operators divided by the derivative of the calibration curve with respect to the parameter. And this is very simple. Now let's look at the case where we want to use the information contained in all the modes that we can measure. And in this case, we can do the same procedure, but instead of considering single measurement results, we consider a linear combination of measurement results. You can see that here I'm talking about mean values, and since mean values are linear, and I consider a linear combination of measurements result, I can do all my measurements independently and then take the linear combination of all the mean values. It's equivalent of measuring a linear combination of an observable. And then we propagate the error into the mean. Now what we can ask ourselves is, what's the best linear combination that I can take? So what are the best coefficients that I can use to minimize my sensitivity? And this can be found analytically. And we define this quantity, which is called the moment-based sensitivity, which is the minimum over all the possible linear combination of basically the inverse of this quantity. So derivative squared divided by this variance of the measurement of rate. And we see that this minimum is given by this kind of sandwich. Now I've written it is as a sum, but it could be written in vector form as a sandwich of these derivatives of our mean values with the inverse covariance matrix for the different measurement observables. And this is the optimal sensitivity that we can obtain with this method, and the coefficients that allows us to reach this optimal sensitivity are simply obtained by multiplying the inverse covariance matrix with this derivative vector. And here it's of course wrong. I should sum only over L, not over K and L. Sorry about that. This method only use information contained in mean values. It doesn't use information contained in higher moments of the probability distribution of our measurement results. So in general, this moment-based sensitivity doesn't saturate the Fisher information bound. However, for separation estimation with SPADE, we proved that this moment-based sensitivity is equal to the Fisher information. And since we know that the Fisher information for SPADE is equal to the quantum Fisher information, this means that with this very simple estimator, we cannot, in principle, saturate the ultimate resolution bound. However, when we do things in practice, our measurements are never ideal. And in particular, for spatial mode multiplexing measurements, what we have is that our apparatus, it's not perfectly aligned with the optical axis of our imaging system. So there is some misalignment between the centroid of the sources and the optical axis of our demultiplexer. Then the demultiplexer is not perfect. So we want to demultiplex in Hermite-Gauss modes, but we will demultiplex in some modes which have a slightly different shape. Or in other words, if we have a signal that should be only in one Hermite-Gauss mode, we will also get some crosstalk, so some signal into other Hermite-Gauss modes. And on top of that, we can, at the detection stage, we can have dark counts. So these are counts that we get which are not related with the signal coming from the sources. It just comes from the electronic noise of the detectors. So these are additional counts that contains no information on the sources we want to characterize. But in this case, we can still use the method of moments. We just need to calibrate our system now using a noise-informed calibration curve. So we need to characterize as best as we can these noise sources. And then we build a calibration curve that takes these noise sources into account. And if we do that, we can compute the Fisher information, or analogically the moment-based sensitivity for this kind of noisy SPADE measurement. And we see that the Rayleigh curve is back. So now this Fisher information goes to 0, but still we have a region where it's better than direct imaging. And maybe another comment here, I'm looking at the Fisher information on using only two modes. So let's say U00 and U01. And so this is not enough to reach the quantum Fisher information bound for very large separation. In this separation, we need the larger modes that contains information on these larger separations. But for small separation, just looking at these two modes, so the fundamental mode and the first excited mode, it's enough to see. In the ideal case, would be enough to approximate the quantum Fisher information. In presence of noise, it's not enough. But still, we have this region here, which is pretty broad. It is in the subdiffraction domain, so we see that we are looking at separation much smaller than the width of the point spread function, where even with noisy spade, we cannot perform a direct imaging. So now let me define a different quantity, which is useful to understand the resolution limits, because when we looked at the Rayleigh limit, or analogously the Abbe or the Sparrow criterion and so on, all these criteria define a minimal resolvable distance. So they say that if your two sources are closer than this separation, then you cannot resolve the two sources anymore. You don't know what's the separation between them. Well, you cannot distinguish them from a single one. And we can try to define a metrology-inspired minimal resolvable distance. And we can do that in terms of a sort of signal-to-noise ratio. The signal-to-noise ratio would be defined by the separation between the sources and the error in our estimation of this separation. So we say that two sources are resolvable if the error that we make in estimating the separation is smaller than the separation itself. And so we define this minimal resolvable distance as the distance for which this ratio is equal to 1. And this 1 over the error, we can express it as the total number of detected photons times the Fisher information, and we take the square root. And then we can solve this equation for d mean. In general, we cannot do this analytically, but we can always do it numerically. Now, if we look at this quantity, d mean, for different measurements, so here you see we have ideal direct imaging, and since since the Fisher information goes to 0, like this square, we find that the minimal resolvable distance for direct imaging scales like the number of detected photons to the -1/4. On the other end, for ideal spade, we had the Fisher information is constant, and so we have that this scaling goes like n to the -1/2. So we can resolve much smaller separations with a fixed number of photons. And here we also see, in a sense, how little sense does the Rayleigh limit make, because this is an arbitrary distance which is defined independently of how much light we detected. And here we see that even for a relatively low number of detected photons for these ideal measurements, we can get far below the Rayleigh limit if we use the proper statistical tools to analyze our measurements results. Now, if we look at noisy spade, if we have if we detect a small number of photons, then because we didn't acquire a lot of information from our system, then the minimal resolvable distance will be large. And then we get into a regime where we didn't enter the region where the the noisy Fisher information is going to zero, and so we approximate the ideal scaling. On the other end, for larger n, we have more and more signals, so we can go farther into the diffraction, the sub-diffraction region. We go to smaller and smaller separation, and at some point we will hit the noise threshold where the noisy Fisher information start going to zero. And so since this noisy Fisher information also goes to zero like d square, as it does the one for direct imaging, we will end up to have the same scaling with the total number of detected photons as direct imaging. But even if we have the same scaling, we have this constant factor here, which can give a substantial advantage in estimating small separations as compared to direct imaging. So what this comparison shows is that, as I said at the beginning, the Rayleigh criterion is a purely geometrical and gives an intuitive indication about the diffraction limit, but it doesn't take into account at all the intensity of the signal and the noise in the signal that we are measuring. So using a metrology-inspired approach, we have a lot of room for improvement. We can go a lot below the diffraction limit, even just by doing a proper statistical analysis of a direct imaging measurement. And we can go even deeper below the diffraction limit if we use optimal measurements like spade, even in a noisy scenario. Okay, now that we have built all this machinery, we know what are the optimal measurements to perform. We have a simple estimator that we can use even in noisy scenario to reach the best possible sensitivity limits allowed by our imperfect measurement apparatus. We can see how we can test this in practice. And so I will do that by looking at a demonstration experiment. So there is a very vast experimental landscape on this subject. So these are some experiments. This is not a complete review of all experiments, but let's say these are some experiments where spatial model multiplexing was not exactly implemented, but some approximation of spade have been implemented using some other interferometric techniques. Then there is a class of experiments that implemented real spatial model multiplexing measurement using multiple modes. And all these experiments used a technique which is called multiplane light conversion to implement these spatial model multiplexing measurements. What's multiplane light conversion? Well, multiplane light conversion is a technique that allows to implement arbitrary unitary transformations between spatial modes of light. And it does that by combining free space propagation and phase transformation. So by applying successively different phase transformation, you can map arbitrary modes in arbitrary modes by designing the phase plates appropriately. And there are commercial devices which can be bought that implement this kind of transformation. These are mostly produced by the French company Skylabs. This is a spin-off of the group of Nicolas Treps at Laboratoire Castel-Bruxelles in Paris, where I was working up to 3 years ago. On the other end, these devices can also be implemented by doing multiple reflections on some phase manipulating device, like spatial mode modulators or deformable mirrors and this kind of things. And there are many laboratories that do that, let's say, in-house. So they don't buy these devices, but they implement the transformation by themselves. So these 5 experiments, they used multiplane light conversion to look at separation estimation of 2 incoherent light sources using spatial mode multiplexers. And all these experiments, they use multiplane light converters from Skylabs. This experiment was performed by the group of Mankitsang in Singapore. These 2 experiments are from the group of Nicolas Treps in Paris, and these 2 experiments are from the group of Cosmo Lupo at the Politecnico of Bari in Italy. I will focus on this experiment in the following, and there are 2 main reasons. One is a very egoistical reason. So I was part of this experiment, so I know it very well. And the other reason is that it is the experiment where the highest sensitivity has been achieved. So this is the experiment which proved the highest violation of the Rayleigh limit up to date. So I think it's also an interesting experiment from this point of view. But all the other experiments are also great experiments, and you're very much invited to look at what these other great researchers did. So how does our experiment look like? So we start with a continuous wave laser at 1550 nanometer. So this is a telecom wavelength. And then we go through this is a fibered laser. So all these yellow curves are optical fibers. And we have this fibered part, which is our incoherent source generation state. How do we generate these incoherent sources? Well, we use phase and amplitude modulators to randomize the amplitude and the phase of the light which enters, which is in these 2 fibers. And if we wouldn't do that, since these 2 paths originate from the same laser, they would be coherent. And so when we combine the 2 paths without any modulation, we would obtain these kind of interference fringes. On the other end, when we turn on our modulators and we completely randomize the amplitude and the phase, then we obtain this kind of pattern here where we see there is no interference. So we can, in this way, emulate 2 incoherent Gaussian spots which simulates the output of a diffraction limited imaging system. And then here we have this part here where we get out of the fibers and we recombine the light on a single path. So we have our 2 incoherent images propagating together. And here we go to the multiplane light converter where we perform the measurement into the Hermite-Gauss basis. And here we have a quadrant detector that we use for position control. Let me open up. This is a picture of how the experiment looked like in the lab. So here you see we go out of the fibers. We have the 2 incoherent sources that we recombine on this beam splitter. Here there is the path that goes to the multiplexer, and here there is the path that goes to the quadrant detector. Now, why do we use this quadrant detector for position control? Let me open a parenthesis of these devices, about this device, which is almost optimal to estimate the position of a single source. So first of all, what does this device do? It measures intensity. Well, it's basically cut in half, and it will measure intensity on this half and on this other half. Now we look at the quantum state of one photon in a mode U0 that might be shifted with respect to the optical axis. And we want to compute the quantum Fisher information for the estimation of the position of this beam. And we do the calculation as we did before for the estimation of the separation between the two sources. In this case, the calculation is much simpler. This term is 0 because we have only the shape of the mode that depends on the separation. Then we can again calculate the Hamiltonian. And again, the Hamiltonian will have only a term which depends on the populated modes, which in this case is only one mode. It's the shifted mode. And so we only have a vacuum contribution that comes into the quantum Fisher information, which is proportional to the modulus square of the derivative of the shifted mode, and we obtain this value of the quantum Fisher information. Now, as I said, we use the quadrant detector as a split detector, so we only measure intensity in one half and in the other half. And we can use the method of moments to look at the optimal linear combination of these two intensities. And if we do that, we see that the expectation, so we know that this is the method, the moments-based sensitivity, and these are the coefficients of the optimal linear combination. But to do this calculation here, we need to plug in this expression for the intensity measured on one half and in the other half of the detector. And since we are integrating Gaussian over half space, we obtain this expression, which looks like which depends on an error function. And for this kind of state, the covariance matrix is diagonal. So we can compute these these optimal coefficients by using this expression. And if we do that, we obtain that in the limit of very small displacement of a beam, the optimal combination is obtained when we take the two opposite coefficients for the two halves of the detector, and we also obtain that the sensitivity obtained from this split detector is just a factor 2/π smaller than the quantum Fisher information. So it's almost quantum optimal. And I find it's very interesting that if we use the method of moments, we obtain this result here. And this result is also actually very intuitive, because if you have your spot, which is centered between the two halves of the device, as you move away from the center of the device, you will get a difference in the photocurrents, which increase at the first approximation linearly with the shift, and so you can directly relate this difference of photocurrents with the shift of your observable and with the shift of your beam. So, and this is a mathematical proof that this is in fact an almost optimal approach to estimate the position of a single beam. And that's why we choose this device in our experiment. So now that we close this parenthesis, we can look at the experimental sequence in our experiment. So first, we perform an alignment stage. And in this alignment stage, we want to align the multiplexer, so the multiplane light converter, with the axis of our two optical sources. So we would like the centroid of our optical sources, even when we start shifting them, to be aligned as best as possible to the centroid, to the optical axis of the MPLC. And to do that, we use all the modes that are available to us. So these are 5 modes. And what we do, we try to basically minimize the intensity in all these higher order modes. And having access to all these higher order modes, and even the modes which are orthogonal to the direction where we displaced our source, is crucial to get a very good alignment. Then we move to the calibration part, and the calibration we perform using only one source. So we take one source, we start shifting it around in the transverse plane. We measure its position with the split detector, and then we measure the intensity on the multiplane light converter. And then we know that when we will have two sources which are symmetrically displaced with respect to the optical axis, the intensity we will get here would be double what we get for one source, and the separation is equal to, well, twice the shift that we measured with the split detector. And then we move to the actual measurement part, where what we do is we turn our sources on one by one, and we measure their positions with the split detector. So first source, second source, then we turn them on at the same time, and we measure the intensity only in the first excited mode. And this is because we showed before that for very small separation, this is actually the only mode that matters. So in this way, with this sequence, we acquired our ground truth on the separation with the two measurements with the split detector, so these two measurements, and then we acquire our actual measurement that we use for the estimation from the multiplexer. And we consider both sources with a width of 1 millimeters, and then we perform the experiments in two regimes. One is a low flux regime, where we integrate for 100 milliseconds. So since we have this low flux of only 50 femtowatt, we need a longer integration time to detect about 3,500 photons. On the other end, when we go to the high flux regime, we have this much higher power. Then with only 5 milliseconds of integration time, we can acquire 10 to the 13 photons. Then, as I said, we use this single source calibration, and then we repeat these measurements. So these 100 millisecond measurements and these 5 millisecond measurements 200 times to be able to get the error bars on our sensitivity, on our estimation. So let's start from the results in the low flux regime. So if we look at, this is the plot of the estimated sensitivity as a function of the width, I mean, in units of the width of the point-spread function, or in micrometers as a function of the reference sensitivity, so the ground truth that we measured with the split detector. And we see that here we have quite nice linear correspondence. So our results are quite accurate. And if we look at the error bars, these are of the orders of 30 micrometers for a beam which is 1 millimeter. So we are deep into the sub-diffraction regime. It's 2 orders of magnitude. And if we now compare with the direct imaging, so direct imaging is this red curve here, and we see that we have a regime here for very small separation where we are outperforming ideal direct imaging. So this curve was computed with an ideal direct imaging with infinitely small and infinitely many pixels, no noise, while in our experiment there was clearly noise and equivalent losses. So we assume that the number of photons that enters our multiplane light converter is the same as the number of photons that would be detected by this ideal direct imaging. And we see we are not at the quantum Kramer-Rao bound, but we are quite close to it. Now, let's move to the high flux regime. So in this case, we have many more photons. So the error bars in these plots are not seeable, so visible. And if you look at this plot, you would say, this looks pretty linear to me, looks good. But if we zoom, we see that compared to the size of the error bars, we are quite far from what we would expect to be the ground truth measured with the split detector. So what we see here is that our measurement has some accuracy problem. So we have an accuracy which is of the order of 1 micrometer. So we are 1 micrometer off in a regime of separations which goes from 20 micrometer to 150 micrometers. And why is that? Well, mostly depends on the shape of our calibration curves. That I mean, we are doing the estimation assuming that the two sources are equal, but they're not perfectly equal. So you can see the calibration curves are quite shifted. So the offset in zero has shifted and the minimum position is shifted. So we have some systematic errors that are not taken into account by our estimator, which induce this low accuracy of our experiment in this regime. On the other hand, if we look at the sensitivity, our error bars are of the order of 20 nanometers, which in this regime is much larger than the quantum Kramer-Rao bound. But this is perfectly consistent with the amount of noise that we have in our experiment. So, but here, if we model the electronic noise of our detector, we see that the sensitivity of our estimations it falls almost exactly on this line. And so the sensitivity is 5 orders of magnitudes better than the beam size, so 20 nanometers compared to 1 millimeters, and it's limited by the electronic noise of the detector. Now, what we asked ourselves is this very high sensitivity useful if our accuracy is not as good? And so what we did was some differential measurements. So we started from a certain level of separation, and then we started changing this separation continuously, and about with steps of 250 nanometers, and we looked at how our estimator behaved in this case. And what we see here is that we have a quite good linear correspondence. So even if a single measurement is not accurate, our estimations are all shifted in the same direction in a sense. So we cannot accurately estimate a specific value of the separation, but we can estimate with very high precision. So with our sensitivity, which is 5 orders of magnitudes below the diffraction limit, we can estimate a variation of the separation. So even if our accuracy could be improved, and actually is already improved in the next version of the experiment, but even with the lower accuracy that we had in this experiment, we can still exploit this very high sensitivity for differential measurements. Yeah. So I've concluded this part on the experiment. Let me give now a quick overview on some other problems that we looked at in this context. And first thing I want to discuss is what happens if there is some mutual coherence between the sources. So if you have a laser, you normally have oscillations like this, which corresponds to an infinite coherence time, but okay, technically this should move, but it's fine. In practice, there are some phase fluctuations that will cause this perfect oscillation to fluctuate in time. And when we have two different sources with different phase fluctuations, it's the correlation between these phase fluctuations which determines the mutual coherence between these two beams, these two modes, and so on. And this is usually quantified by this degree of mutual coherence. And if we have incoherent sources like the one we were considering before, when in the experiment, we completely randomized the phase to obtain this value of the mutual coherence equal to 0. In the other end, if we have two perfectly coherent sources, then their phase noise will be perfectly correlated, and this means that the amplitude of this degree of mutual coherence is exactly equal to 1. And but this quantity is generally a complex number, this degree of mutual coherence. And when we bring coherence into the description, then this induces interference, and interference has an impact on possible resolution limits. So if we look at these Rayleigh kind of plots, and here we have two coherent sources which are perfectly in phase, so they interfere constructively, we see that when we bring the sources closer to one another, this intensity, they perfectly sum, and then you get a very high peak when the sources are very close to one another, and this makes them harder to distinguish, even harder than two incoherent sources. On the other hand, if we have two sources that interfere destructively, we always get a minimum at the center, even if when they are very close. So it's always simpler to say that these are two sources and to estimate the separation. And this coherence very often appears in practical scenarios. For example, if you illuminate a sample with a common coherent source, and then this source has a finite coherence width, and this induces some mutual coherence between the sources. And or if you look at two interacting emitters, the interaction induces some mutual coherence. And what is interesting is that these mutual coherence generally depend on the separation. So in this case, when we look at the common source with finite coherence, we have that if the two sources are very far away and the separation is larger than the coherence width, then they will emit basically incoherently, while for small separations, which are smaller than the coherence width, the two sources will emit basically coherently. So we get this kind of Gaussian dependence of the coherence between the two sources with the separation. And here the interaction strength between these two emitters might depend on the separation, and this gives some mutual coherence that depends on the separation. And so we have some additional dependent on the separation, and we can use this additional dependence to boost the resolution. For example, if you look at the reflection from a common source and we look at the method of moment sensitivity, we see that in the incoherent case, you had this constant at 1. Now we have the two coherent sources that for very small separation, they will always emit coherently. Oh, sorry, wanted to go back. And we say that when they emit coherently and in phase, we have this constructive interference that makes the problem harder. So we always have this kind of Rayleigh curves, but for intermediate separation, we get this very high peak that comes from the dependence on the mutual coherence with the separation. And this peak is usually for separation of the orders of the coherence width of the common illumination. On the other hand, if we consider interacting dipoles, then we have some fluctuations of the interaction strength with the separation, and this kind of dependence introduce some oscillation of the total sensitivity, which can be very large depending on the interaction strengths. So if we have a separation-dependent coherence, it's something that we can exploit to boost resolution. Finally, I want to move to a different problem, but which is very similar to what we discussed so far. So far, we always say, okay, there are two sources and I want to estimate the separation between them. But if we are at separation which are much smaller than the diffraction limit, sometimes it might be hard to know if there is one source or two. So you get a signal and you assume that it comes from two sources, you do your separation estimation, but maybe this doesn't make sense because in fact there is only one source in the object plane. So another interesting problem is to do hypothesis testing. So to test if between two hypotheses and decide, is there one source or there are two? And in this problem, there are two errors that one can make. One is a false alarm kind of error, which is assuming that there are two sources where in fact there is one. And the other one is a miss kind of error, where you assume that there is one source where in fact there are two. And in this case, I want to consider only symmetric hypothesis testing. So when I give the two probability of errors the same importance, and so I define my average probability of error as the quantity of interest for this problem. And this probability of error can be approximated in the asymptotic limit by the so-called Chernoff bound. And we have a classical Chernoff bound which tells us that the probability of error decays exponentially with the number of detected photons with this rate, which is called the Chernoff exponent. And in a way which is very analog to what we do with the classical Fisher and the quantum Fisher, we can optimize Chernoff exponent over all possible measurements allowed by quantum mechanics, and we obtain a quantum Chernoff exponent. And if we look at the Chernoff exponent for direct imaging, this scales like the separation to the power of 4, while the quantum Chernoff exponent, which is equal to the Chernoff exponent for spade, it scales like the separation to the power of 2. And for ideal spade with no noise, there is a very simple statistical test that you can do, which is you look at one mode, let's say this one, and if there are photons in this mode, then you decide that there are two sources. And this is because if there is only one source, you're perfectly aligned and everything is perfect, then you get a signal only in this mode. So one of the two error probabilities is always 0 if if you just look at this mode. However, if we consider noisy spade, then situation is not so simple. We get, as we saw before, for a minimal resolvable distance, that we go back to the scaling of direct imaging, but still we get some advantage. What is more surprising is that for arbitrary small amounts of noise, this test here become completely useless. So this test has a probability of error of 1/2. So it becomes as good as flipping a coin. In arbitrary of any small amount of noise. So as soon as you have a finite probability of detecting photons in this mode, even if there is only one source, then this test has 1/2 error probability. So you can just not do any measurement and just guess, and you will obtain the same result. So what we did with my colleagues was to design an optimal test that has a noise adapted threshold and which also works in noisy scenarios. And these tests look like this. So we have this part here where there's n times p0, where p0 is the probability of detecting a photon in the monitored mode, even if there is only one source. So this should be h1, not h0. And naively, one might think that this threshold here would be enough to adjust our test to the noisy scenario, but it's not enough. If we just change the threshold from 0 to np0, we obtain an error probability of 1/4, which is better than 1/2, but still not very good. And so we have to add to the threshold this term here, and this term here depends on a minimal distance we're interested in. So we say that, so what we are in fact testing is there one source or two sources at a separation which is larger than the mean. And if we perform this test, then we obtain these error probabilities, and we see if that our separation is exactly equal to the mean, that's the blue curve here, then the solid line coincides with the dashed line, and the dashed line would be the quantum limit. In all other cases, for separations larger than our d mean, we have an error probability which is larger than the best that we could obtain, but still we have this blue line that we can always use as an upper bound on the error probability. So we always know which kind of errors we are making. And on top of that, in the asymptotic limit, all these curves, they coincide. So in the asymptotic limit, we are quantum optimal. Okay, so that's everything I wanted to tell you today. And before answering your questions, I wanted to thank all my co-workers. Claude and Nicolas have been mentors, teaching me a lot about states and modes in quantum optics. Mattia and Manuel contributed mostly to the theory of mode-encoded parameter estimations. David, Clementine, Antonin, and Alexander, they're mostly doing experiments, and they are the main people who did the experiment I showed you before. Tomasz, Konrad, and Lukasz from the University of Dansk, they contributed to the work on hypothesis testing, and Ilya was the main theorist who worked on the work on separation-dependent coherence. These are some references on the things I told you before, and a more complete list of reference on this subject. You can find it on the blog of Monkey-san. So thank you for your attention, and now open for questions.
Thank you very much. Thank you very much. So we have time for questions locally. Has somebody here? We have.
Thank you for this brilliant talk. I wanted to ask a question. So, in the beginning, so correct me if I'm wrong, but I think you just derived these results used the fact that in each mode you have at most one photon, right?
Yes.
But of course, it's as far as I know, it's not realistic. So, is it possible to extend these results to a case where you have many photons in a mode?
Yes, it is possible. So here, for simplicity, I only consider the case where you have 1 photons per mode, and here I'm talking about the image plane. So in many cases, you will have at most 1 photons per mode. If you think about astronomy, where light comes from very far away, most of the light is lost coming through the telescope, and for each detection event, you will always have very few photons. But we extended, I mean, already Monkey-san, and there is also paper from Cosmolupo where they extended the results to arbitrary thermal states, and then actually these works, we did them also for thermal states of arbitrary intensity, and our theories for estimation of parameters encoded in 2 modes, they can be applied to arbitrary quantum states, and most of the results remains the same independently of how many photons you detect per mode. It's just that the math for a lecture was much simpler, just considering 1 photon per mode.
Yeah, thank you. Thank you.
Thank you. Another question? Microphone.
Thank you for your talk. I have some curious question. So when we considered, I believe, Hamiltonian, we separated it to the vacuum and interactive parts, and I believe we crossed or just simplified the interactive part. Can you please clarify how did we done that? I didn't get it. Yes.
You're talking about the expression for the quantum Fisher information. Is that correct? When we define this Hamiltonian, and then we go to the and then we divide the Hamiltonian into the vacuum part and the populated modes part. Is that correct?
Yes. So
okay.
About that part.
Yeah, I'm going back to that slide. Okay. Let me. Oh, sorry. Let me just reshare my screen. Nope. It's kind of okay. I do like this. I hope it doesn't take too much time. Yeah, so we are here. Yeah, here. So here we define this Hamiltonian, this generator, and this is defined over a complete basis. So technically, I mean, it has infinitely many terms, but not all modes play the same role in these expansions. So if you fix a value of the parameter, let's assume that we consider that the separation is 0, and we want to estimate a small variation around 0. Then we have some modes which are populated for this value of the parameter, 0. And then there are some other modes that for this specific value of the parameter are in vacuum, but that will get populated when you slightly vary the parameter. And that's the criterion that we use to do this separation in the Hamiltonian. So these are the modes that are populated for a specific value of the parameters. And these are the modes that for that specific value of the parameter are in vacuum. So you consider a specific value D of the parameter, then these are the symmetric and antisymmetric superposition of these image plane modes. And these are the only modes which are populated for that specific value of D. And then all other modes, higher order modes, will be in vacuum.
If I was correct, because they are populated, we are not interested in them. Am I right?
Sorry, I couldn't hear you well. Could you
So
repeat it?
if I understood correctly, we are not interested in that part because they are already populated. They would not provide any information for us, or is that the idea?
So I wouldn't say that they do not contain information, because here we're looking at variations of the parameter. So when the parameter slightly change, some population goes into these modes. So in fact, they contain some information, but the fact that this small amount of information leaks into this mode, it's what tells us that it's actually the noise into these modes that has an impact on the sensitivity. So these are the modes where most of the information, well, in fact, these modes, these modes, they contain no information on the variation of the parameter, and all the information on the variation of the parameter is contained in modes that for a fixed value of the parameter are in vacuum. And it's the noise in these modes that determines the sensitivity.
Oh, okay.
Okay, take the microphone. Okay, one more question.
Thank you for your talk. So my question is, to decide which modes are the optimal ones, if I understand correctly, we derive that from the point spread function. So the
Exactly.
question would be, and if I understand correctly as well, in your experiment, you basically simulated the point spread function so that your optimal modes are Hermite Gaussian modes. So the question is, if we want to use this as an actual detection tool, for example, in astronomy, we will have an actual say telescope with its point spread function. Do we so there are like two sub questions here. The first one, how do we get those optimal modes? Do we do that numerically, or and the second sub question is how hard it is for an arbitrary apparatus to design a measurement apparatus that measures on those specific modes?
Yeah. Okay. So the first part of the question is if I mean, we have a specific device, a microscope or a telescope, and in a telescope you might have obscurations and all sort of mirror arrangement that give you a point spread function which is not a Gaussian. It might be something more complicated. how do I find the optimal modes? So two parts of the answer. So one way for a single parameter estimation, so you want to look just at the separation, the optimal modes are simply constructed by orthogonalizing derivatives of the point spread function. So here we started from a Gaussian, we took the derivatives with respect to x, and these derivatives are the Hermite Gaussian modes. And these come from this Taylor series kind of intuition on why these modes might contain more information. Already when you look at multi-parameter problems, finding an optimal basis, which is optimal for multiple parameters, assuming that you don't know any of them, it's a very complicated task, and a precise recipe for doing that, it's not known at the moment. And there are several people working on that. The second part of the question is, once I know in which measurement, in which basis I want to measure, how do I implement these measurements? And these is, I had it in the experimental part. It's probably a more efficient way to change slides, but it wasn't working at the moment. Okay, so the technique that that one can use is this multiplane light conversion here. So this works really to map arbitrary modes into arbitrary modes. And what is usually done for the multiplexing is to map the modes you want to demultiplex into spots, which are located at different positions. And then, for example, in the commercial devices, you couple the different spots into different optical fibers, so you just plug the fibers to your detector. But there are deterministic algorithms, numerical algorithms but deterministic, that you can use to find the phase transformations that maps n arbitrary modes into other n arbitrary modes. This can be done very efficiently, and then depending on the number of modes, the kind of modes you have, you might need to use more phase transformations, or you might need to adapt the separation between the phase plates and these kind of things. But in principle, every transformation is possible, and there are very efficient design algorithms to obtain these devices.
And now
we can maybe shift more question to a person or to three microphones. Sure. Yeah, because because of time, but Giacomo, this is not the end. Let's say, Anton, do we have online question?
Yeah, we have online questions. I have a proposition that we declare the coffee break, and I'll ask the questions during the break, basically.
We have a free microphone here, Giacomo, so students during coffee break may come, so we can ask you maybe to be here next 1 or 2 minutes, or maybe a little bit.
Absolutely.
And let's say our speaker again. And if you want, I will rotate this camera, okay? And you can ask directly here. Thank you very much, Giacomo.
But you need to be very quick, because the next lecture starts in 7 minutes. So yeah.
Yeah.
So we cannot start in 7 minutes.
Okay, let's do in 10 minutes then, okay?
15.
Yeah, so
Alex.
Because it's okay, we will try. We'll do all the best. Okay. Yeah.
do you hear me now? Is it good?
I can hear you, yes.
So I come from a quantum computing background, so right away the question I have, this apparatus that you basically have some basis that is easy to measure, and you implement unitary transformations to measure on any basis. So the question that occurred to me is this apparatus is basically a quantum computer. So if you want to like implement any unitary transformations, so the question becomes, when you want to go to when you want to go to best resolutions, you want to have as many modes as possible. And to me, the issue becomes that to implement that like arbitrary unitary transformations on many modes, it's basically as hard as to make a many qubit quantum computer. Is that an issue? Like if you want to have not 5 modes, but say like 100 to get the best resolution possible.
So there are two parts of your question. So you say that to get the best resolution, one needs to measure many modes. This is not completely correct. So if you want to estimate few parameters of an object, then the idea is to find the smallest number of modes possible to extract these parameters efficiently. And in general, for very small separations, if we want just to estimate the separation, this we can do with only one mode. So, and if you increase the number of parameters, you need at least as many modes as parameters. But if your problem is not too big, then you can deal with it by just measuring an optimally designed number of modes. And this is in a sense similar to what people in classical computational image processing do when they do compressed sensing, so that you have a problem which is defined by a very large number of parameters and or in a sense basis elements, and then you, by doing some sort of eigenvalue decomposition of the problem, you just restrict yourself to the basis elements with the largest eigenvalue, and you get in imaging you can compress images in a way that you can't even see the amount of information that has been removed. And then regarding the analogy with the quantum computing, I think, I mean, a difference here is that here everything is linear. So this is just linear unitaries.